Hello, welcome back. We have been looking at Maxwell's equations, and we saw that Maxwell's equations were able to show us that we can have a self-sustaining electromagnetic wave, and that light is in fact an electromagnetic wave. Then we started to look at the properties of electromagnetic waves. We're going to continue talking about some of the properties of electromagnetic waves and look at a very specific issue with electromagnetic waves, that we can actually polarize electromagnetic waves. Here we see an electromagnetic wave that is traveling along the x-axis. So it is moving in this direction, which is why we see it's moving here with a speed v e sub em, which we know is equal to c, the speed of light. So this is a sinusoidal wave, and it has frequency f, and here's the wavelength that goes from one crest to the other here for the electromagnetic field. And that electromagnetic field is completely, perfectly perpendicular to the magnetic field. So E and B are perpendicular to each other and to the direction of travel. And we see that E and B are in phase. That means when E is at a maximum, B is at a maximum. When E crosses the zero, B crosses the zero. When E is at a trough, B is at a trough. They are perfectly in phase. And the other thing we see is that the field strengths are related by E equals CB at every point on the wave. So that works even when E is zero, B is zero. And the direction of E cross B is in the direction of VEM. So the direction that the wave is traveling is in the direction of E cross B. So what we can define here is what's called the Poynting vector, and it is in the direction of E cross B, so it is in the wave direction. The energy flow of an electromagnetic wave, that's the direction that the energy is flowing in the wave direction, and that's described by the Poynting vector, where S is the Poynting vector, is defined as 1 over mu naught of E cross B. And we can take our right hands and put our fingers up in the direction of E, have our fingers curl down in the direction of B, and we see that our thumb will then point in the direction of S, which is the wave direction. Now, if we want to figure out the magnitude of S, we would say the magnitude of S in that case would just be equal to E times B over mu naught. Now we remember that E equals CB. So I can rewrite this as, I can divide both sides by C and say that E over C equals B. And putting that in here for E, I can then rewrite S as equal to E squared over C times mu naught. And since E varies from, as we saw, it goes from 0 up to E naught and back down to 0. So that the max E can be is E naught. So that means that S max will be E naught squared over C mu naught. So S will also vary from 0 to E naught squared over C mu naught. The Poynting vector always points in the direction in which an electromagnetic wave is traveling, which is the direction that the energy is moving. The units for S are watts per meter squared. And the magnitude of S of the Poynting vector measures the instantaneous rate of energy transfer per unit area of the wave. So that's what this is. Watts is a unit of power, which is a rate of energy transfer. And then meters squared is the area, the unit area of the wave. The Poynting vector is a function of time, just like the electric field and the magnetic fields themselves. It oscillates from 0 to S max equals E naught squared over C mu naught, and back to 0 twice during each period of the wave's oscillation. Now, that's helpful to know what its max is, but of more interest is the average energy transfer, which is averaged over one cycle of oscillation, which is the wave's intensity I. So if S max is E naught squared over C mu naught, then we can see that the average will just be 1/2 of that. So the intensity of an electromagnetic wave, we know intensity is power over area. So the intensity equals the power over the area, and that's going to be equal to S average, where S, again, is in watts per meter squared. It is the rate of energy transfer per unit area. So it is the power over the area. So it's the S average, and the average will just be 1/2 of S max. So it will be 1/2 of E naught squared over C mu naught, which we can also rewrite then as C epsilon naught over 2 E naught squared. The intensity of electromagnetic waves at a distance r away from an isotropic source with power P source. So we want to look at the intensity as the power over the area. So if we know the power P source, then we know that that intensity of that electromagnetic wave, when the source is sending it out in all directions, will go out as the area of the sphere. So it will be I equals P source over the area of the sphere, 4 pi r squared, surface area of the sphere. Now, another thing that we can look at when we're looking at electromagnetic waves is we can look at the fact that we can look at the radiation pressure. So electromagnetic waves transfer not only energy, but also momentum. So let's suppose we shine a beam of light on an object that completely absorbs the light energy. So if it completely absorbs the light energy, the momentum transfer will exert an average radiation pressure on the surface. Now we remember that pressure is force over area. And if I want to get this in terms of the intensity and the speed of light, I remember that force over area, that's looking a lot like power over area. But in order to get force to be the same as power, I'm going to need to multiply the top and the bottom by speed, by some sort of force times a distance will be a joules divided by time will give us our power. So we're going to multiply the top and the bottom here by a speed. So multiply top and the bottom by c. And so I can then rewrite this as the power over the area over c. And I see that's the power over the area over c, where the power of the area we know is the intensity, and intensity is the intensity of the light wave. So we can find the radiation pressure as just the intensity over the speed of light. Now, another important thing that we can do with light, and you've all worn polarized sunglasses, you've all seen this when you've gone skiing or somewhere where you maybe fishing and you want to cut the glare, you know that you can wear polarized sunglasses. And what that's doing is it's actually polarizing the light. So let's talk about what that means a little bit. So polarization. So we start here with our normal, regular transverse wave, EM wave here. And in this case, what we see is the plane of the electric field. So it's the plane of the electric field vector, and the Poynting vector S is called the plane of polarization. So it's the electric field vector that gives us our plane of polarization. So in this image right here, the electric field in this figure, is oscillating vertically. So this wave is vertically polarized because it's the electric field that's oscillating vertically, as I indicated right here. So now we could also look at an electric field that's oscillating horizontally. So here's an electric field that's oscillating horizontally. So the electric field is oscillating in the horizontal plane. So in this case, the electric field is horizontally polarized. Most natural sources of light are unpolarized. So they do not have a specific polarization, except as you've noticed if you've gone fishing or skiing, or what else would you have done? You could have gone out anywhere on the water, maybe water skiing, and you'll see that that light, if it is reflecting off the water, it has become polarized. But most of the time it's not, and it's randomly, and the electric fields oscillate randomly with all possible orientations. So if we want to, we can polarize that light. So we can take unpolarized light, which consists of waves polarized in all possible directions, and we can put it through a polarizer, which is made up of different polymers, and it only allows the component of the electric field that is parallel to the axis to be transmitted. So this one is going to be horizontally polarizing the light. So the most common way of artificially generating polarized visible light is to send unpolarized light through a polarizing filter. So now let's see if we can actually quantify what light goes through that polarizer. So that's where we come to Malice's law. So suppose polarized light of intensity I naught, so it starts with its intensity I naught, approaches a polarizing filter. So here it is coming in. The incident light is polarized at angle theta with respect to the polarizer axis. Only the component of E that is in the direction of the axis is transmitted. So the component of the incident electric field that is polarized parallel to the axis is transmitted. So just the component that is parallel. And we can see that this component is E naught cos theta. So E transmitted will be what's E parallel, j hat in this case, and that's going to be E naught cos theta j hat. The transmitted intensity depends on the square of the electric field amplitude. So the intensity that is transmitted will equal I naught cosine squared theta. And that is Malice's law. Now, Malice's law can be demonstrated with two polarizing filters. The first, called the polarizer, is used to produce polarized light of intensity I naught. The second, called the analyzer, is rotated by angle theta relative to the polarizer. So what we see when we do this is the transmission of the analyzer is ideally 100% when theta equals 0. So here we have theta equals 0. The light is going through the first polarizer and then through the analyzer. And if theta equals 0, then all the light will pass through. And it will steadily decrease to 0 when theta equals 90 degrees. So here we go to 45 degrees, we have less light transmitted, all the way to 90 degrees where no light is transmitted. So two polarizing filters with perpendicular axes called cross polarizers block all the light, like we see right here in this example. If the incident light on a polarizing filter is unpolarized, half the intensity is transmitted. So I transmitted equals 1/2 of I naught. And that's how much intensity of light can get through when we have a polarizer. So polarizing light, as we know, can be used for polarizing glasses and is a way of getting the electric field to go in just one direction instead of going in all different possible orientations. So light as a transverse wave has some very interesting properties. And what we saw is that the intensity of light is very important to figure out how much energy is transmitted, and we can find out its radiation pressure. And then we can use polarizers to actually diminish that intensity and get the wave propagating in only one particular polarized orientation.